now we have Professor Holger Dullin from University of Sydney speaking about Lagrange top and Confluent Heun equation.
Yes, thank you very much for the opportunity to speak here once again. Thanks to the organizers, to Alini, Milena, and Sean. I will talk about a very classical subject, or two actually very classical subjects, the Lagrange top and the Confluent Heun equations and their connection. And we've already seen, well, some talks, I guess it was in Harini's talk, where maybe the Heun equation was lurking in the background. And I'll come back to that at the very end, but mainly as an open question. Anyway, so let me begin. I'll just give you a brief introduction and then the main statement, and then I will go into the details. So you can see the Lagrange top at the top right here. It's a kind of state that is almost a periodic orbit, where the top is just spinning. The contact point here on the table should actually be fixed, because the idealization is that this is a rigid body with a fixed point. It's a symmetric rigid body, and the center of mass of this object is somewhere on the symmetry axis, but not at the fixed point. So that's the description of a Lagrange top. And so the system has two symmetries, rotating the body, and it also has gravity is acting. And if you rotate space about the axis of gravity, that's another S1 symmetry. And because of these two symmetries, we have two conserved quantities, and we have a Liouville integral system on the cotangent bundle of SO3. And just a bit of notation that I'll use later on. So these vectors L and A, the three-dimensional vectors, the angular momentum and the figure axis on the top. And one slightly unusual aspect of my treatment of the Lagrange top is that I will do everything in the spatial frame. Usually you do rigid body dynamics in the body frame for good reason, but that reason doesn't apply to our case. And so we can easily write down the Hamiltonian, and I'll explain this a bit more later, in terms of these spatial quantities. So it's L squared, angular momentum squared. Then there's a kind of correction factor here, delta. Delta measures how non-spherical this body is. So if all three moments of inertia, I1 and I2 are equal already, if the third moment is also equal, then delta is 0. Then we have the spherical top, and then this term disappears. And then there's some potential that depends on the Z component of the figure axis. So in gravity, this is just a linear potential, but I want to be slightly more general than that in this talk. Okay, so much for the Lagrange top. Now the Confluent Heun equation. So Confluent Heun equation is a second order linear equation in the complex plane. Or ideally, one should think of the Riemann sphere. And the Heun equation is a Fuchsian equation that has four regular singular points. So there are four punctures on this Riemann sphere, and it is the natural generalization of the hypergeometric equation. So for the Confluent Heun equations, you take two of these singular points and coalesce them, and that creates an irregular singularity, and that's usually placed at infinity. And then here's the equation. So there are the two finite singularities at 0 and at 1. To these points are associated some indices that describe the local behavior that's encoded in these parameters gamma and beta. There is this parameter Q, which is called the accessory parameter, and then there are two more parameters, epsilon and alpha. So these are just constants. Okay, so it's a simple linear differential equation, slightly more complicated than the hypergeometric equation. And the point of my talk is to say that when you quantize the Lagrange top, but with the potential that also has a quadratic term. So not just the usual linear term, which is the top in our physical space, where we just have gravity acting, which is a linear potential, add a quadratic term, and then quantizing that system leads to the most general Confluent Heun equation. Okay, that's the main statement, and now there's a simple corollary of that that will be based on the analysis of the classical system. So as long as the potential is non-zero, then the set of regular values in the image of the energy momentum map is not simply connected. And therefore, the action variables can and do have a monodromy. They're not globally defined. We should distinguish this from the monodromy of the Heun equation. This is called Hamiltonian monodromy. So it's a kind of monodromy of the action variables of an integral system when you consider path in the image of the energy momentum map. And here is a picture. I'll explain this in more detail later on of the critical values in the image for a particular case. And then combining these two, we get the conclusion that the joint spectrum of the Confluent Heun equation has quantum monodromy. And I'll show some pictures of that to illustrate that in the end. All right, so this is the program for the talk to explain these things and how this connection comes about. So I'll talk about the Lagrange top, about the classical system first, and I will describe it in a Poisson structure that at least I couldn't find in the literature so far. So it's a spatial Poisson structure that lives in R7 and that gives a global description of the top. So I guess a lot of this is trying to avoid Euler angles, but in the end, I will need Euler angles to quantize the system. Anyways, so there are these global symmetries, S1 actions that the system has. There are two of them, and we will rediscover them in the Heun equation in a very special way. So that's one of the interesting observations here, this connection. And then I'll discuss the energy momentum map of the system. All right, Confluent Heun equation. I think probably for this audience, I don't need to explain too much about Fuchsian equations and confluence and all that. So I'll go quickly through that. But I will explain how this connection between these global S1 actions, the classical global actions, and quantum numbers and indices of the Heun equation arises. And then I'll have some remarks about how to actually compute the spectrum of the Schrödinger equation, which is the Heun equation. Okay, so let's see. Oh, the top hadn't started yet. Well, anyways, there we go. Of course, it's impossible to give a complete overview of what has been said about the Lagrange top, so I'll just make a few remarks here about the literature. And I'll start with Klein and Sommerfeld, their 4-volume books on rigid body dynamics from 1910 that were recently also translated into English. And there is a recent book by Borisov and Mamayev, which is as monumental, and that has been translated from Russian in 2008. And this is an excellent source of modern theory of rigid body dynamics. So, but the story of the Lagrange top in modern mechanics, let's say, really starts with Cushman and Knurrer, where they describe the image of the energy momentum map. So energy momentum map is simply just the map that takes the energy and the two other constants of motion, and considers this as a map from phase space into R3. And then you study the image of that mapping, and in particular, its critical values. And they observe that this is simply the set of regular values is not simply connected. And I'll explain this again, and we'll see that we get somewhat more complicated versions of this observation. And because of that, then the global action variables may not exist, and they do not exist. That was done for the spherical pendulum, which is a kind of slice of the Lagrange top, if you want. That was done by Cushman and Dijkstermaat in '88. And of course, I should mention Bolzinov and Fomenko and their group, who have also written big book about integrable systems in general, but a lot of examples that they studied are rigid body dynamics, and the Lagrange top is one of the simpler ones, in fact. Integrable discretization for the Lagrange top was done by Bobenko and Suris in a general framework of doing discrete Lagrangian dynamics. Complex geometry has been studied by Gavrilov. The Lagrange top has a bi-Hamiltonian structure that was recently looked at by Tsiganov. And then, of course, it's an integral system that you can perturb, and the KM theory of that has been worked out in detail by Barrera and Hansman in 2006. All right, as I said, in no way is this complete. But let me start now by describing our way of writing down equations for the Lagrange top. And I forgot to mention in the beginning that this is joint work with my PhD students, Sean Dawson and Diana Nguyen, who are maybe in the audience. So it's a system that lives on SO3 as a configuration space, and SO3 is too complicated. So you go to the double cover, which is S3, the sphere. And the natural way to describe the sphere is to just embed it in R4 and to take a point with 4 coordinates, x, 0 up to x3, and say that has length 1. Okay, so that's easy. And now define these 3 by 4 matrices that will just be denoted by x plus or x minus that carry these entries. And with these matrices, you get a factorization of SO3. And you can write the general element of SO3 as x plus times x minus transpose, which is a 3 by 3 matrix. And then you can check that this is indeed an element in SO3. And it is, in fact, the rational parametrization of SO3. So beautiful formula for SO3. You may know these kind of rational parametrizations of the Pythagorean theorem, and this is kind of a fancier version that works for SO3. It's quite similar in many ways. Okay, so now we have a Poisson structure. And for the angular momentum, this is the standard Poisson structure. So the Poisson bracket of Lx and Ly is Lz, and so on, cyclic permutations. And the components of L and these coordinates x, their bracket actually gives back this matrix x plus. And this Poisson structure has a Casimir, which is this length. So we automatically remain on the sphere. A similar Poisson structure has actually been used by Borisov and Mamayev in '97, but they did this in the body frame. And we're doing this in the spatial frame, but there's a lot of similarity. Let me maybe briefly flash up how you actually arrive at this Poisson structure. It's actually a simple computation. So here is, again, the matrix in SO3 written in this factorized form, and here I multiplied out. So this is the rational parametrization. So for any set x0, 1, 2, 3 that has some of their squares adding to 1, this is an element of SO3. So you start in R8, actually, so where x and p are canonically conjugate variables, so with the standard symplectic structure. And then you just write down a mapping from xp to xl, where this L is going to be our angular momentum. And I mean, this is now requires some thought why this is in fact true, but it is a simple map. So I'll just write it down here. So L is, again, this matrix x plus times p, this vector p with components p0, 1, 2, 3. And then you have a Jacobian of this map, which is, again, straightforward. And now you just do a coordinate transformation of your equations that live in this R8 to equations that live in this R7. And when you do that, you get a Poisson structure from the symplectic structure J. And this, the miracle is, depends on X and L only, right? I mean, this in general would depend on P, but the terms combine in a nice way so that it only depends on L. Oh, and I think I forgot a half here. But anyway, so it's a simple computation that leads to this Poisson structure. And with that Poisson structure, now you can write down the vector field of an arbitrary Hamiltonian. And here it is. Okay. So what is the Hamiltonian? Now we have to write down the Hamiltonian for the Lagrange top in these variables L and X. It turns out I'll just use A here as an abbreviation. So this figure axis of the top is just the last column of the matrix R. So RE3, that's our figure axis. I will use this abbreviation. So the x's are sitting inside the R here. Here's our moment of inertia. And now comes the main computation of the kinetic energy. And the reason why you usually use the body frame is that in the body frame, the moment of inertia is constant, while in the spatial frame, it is not. And that you can see here, if you write the kinetic energy in the spatial frame, you basically have to take a product here of R transpose L, which is the angular momentum in the body frame, with the tensor of inertia. And so the R is explicitly in here. And that's bad, or makes things complicated. However, if you have a symmetric body, and notice here multiplied by I1, and here I have I inverse, you see that, well, I almost get the identity matrix here, except in the last component, I will get the ratio of I1 and I3. And so I write this as identity plus that correction term, which only sits in the third column and row. And then you multiply this out and you notice that R times E3 is A, that's the figure axis. And so you can actually write this as angular momentum squared plus the scalar product of L with the figure axis. And so now we've written the kinetic energy completely in terms of spatial quantities. And so this is our Hamiltonian. And you will see that this is also naturally the form of the Hamiltonian as it appears in the Schrödinger operator later. So when we make the transition to the Heun equation, we'll come back to this, this form. Okay, so Lz and L3 are constants of motion. I already stated that, but I guess if you wanted to now formally check that, you should write down the flows that are generated by these constants of motion. And you can do that easily. So the flow that is generated by L3, which is the scalar product of A and L, that acts by rotating, by multiplying the rotation matrix by rotation about the z-axis from the right. And this is now a simple computation because the vector fields of L3 and Lz, they're actually linear in these coordinates. So you just solve them and find this result. And now the flow of Lz is also a rotation about the z-axis, but it acts by multiplication from the left, and it also rotates the angular momentum itself. But you can then check that both of these leave Lz, the z-axis, well, because it's a rotation about the z-axis, it leaves the z component invariant. And the scalar product of L and A is also invariant because we're rotating by Rz from the left, both L and A. And so this cancels in the scalar product. Okay, then the Hamiltonian involves L squared. So you have to check another flow. This also leaves that invariant. And then there's the flow of AZ. And it's easy to check that. Therefore, the flow of H leaves these invariant as well. And so we have an integral system, which is, of course, well known and in most classical textbooks on classical mechanics, except it's usually done in Euler angles. Okay, so now the energy momentum map. So this is a mapping H, Lz, L3 that maps from T star SO3, which you may think of as the symplectic leaf that you get when you fix your Casimir to 1 in this R7 to R3. And we're interested in the rank of this energy momentum map. And for that, you can look at the rank of the 3 vector fields that are generated by these constants. And so there's one simple and intuitive case is when the vectors L and A and Ez are all parallel. Then you have what is called the sleeping top. So that's the one that you saw in the beginning. So here I have a top what you will see in a second is that since this is a fixed point, you usually don't do this on a table, but if it's actually a fixed point, the top can also be hanging, right, from this fixed point. And both of these solutions are sleeping tops, upright and hanging. They're periodic orbits. Then if the three vectors are coplanar in a perpendicular special way, then we have motion on two-dimensional tori. And I mean, this requires some computation, which I don't want to do now. And with this formula, which expresses L as a linear combination of A and EZ, we get a rational parametrization of the set of critical values of this mapping. And otherwise, we get rank 3, so the motion is on 3 tori. So I'm showing you now pictures of the image of this map, and in particular, I'm showing you the critical values of this map. So where we have rank 2 or rank 1. Rank 1 is this blue line. That's part of the rank 1 points. And these are unstable sleeping tops. This line joins this bounding surface, which we cut off at the top here, at these points. And it continues as a parabola, but when they are unstable, when they are stable, which is the rest here, then they are absorbed in this surface of rank 2 values. They still have rank 1, but they have nearby rank 2 points. But the rank 1 points here are isolated. So that's the thread. And the attachment point is a Hopf bifurcation. So now I'm changing C2, this extra quadratic parameter, and I'm making that fairly large. So when C2 is 0, then we have the Lagrange, the standard Lagrange top, and now we have an extra quadratic potential. And it turns out that then the top that is hanging down also becomes unstable. So that's this red line here. And at a certain point, it attaches to the surface. Again, that's the Hopf bifurcation. And when you're beyond the value where it attaches, the surface has a corner, while if you're below, it's a smooth surface. Right? The same is true for the blue line, but here we cut it off, so the attachment point is outside the picture. Okay, so now it gets more interesting when we make C2 negative. So C2 is 0, remember, it's just this blue thread. And when you make C2 smaller than minus a quarter, I believe, then you get these structures appear here. They're called swallowtails. And these swallowtails, they basically eat up this blue thread. And at the end of the swallowtail, where it turns into the thread, that's another Hopf bifurcation, but it's a subcritical Hopf bifurcation. I mean, I don't want to go into this Hopf bifurcation business. It's kind of interesting that in this family, we also get a subcritical Hopf bifurcation. And it is some work to establish that. And I won't have time to talk about that. Okay, and now if we make C2 even more negative, then these swallowtails, they grow together and form a triangular tube, if you want. So we still have this big surface outside, which goes to infinity also, but we always cut it off. Here we also cut off some structure, some part of the surface and the looking at us so that you can look inside, and you see this triangular tube. And the top surface of that tube corresponds to hyperbolic 2 tori, so unstable motions, while the bottoms are stable. Okay, so that's the possible images. And I mean, there's a little thing to prove here that there's nothing else. But the main point I want to make is that in all these cases, as long as C1 and C2 are not both 0, the image of the map is not simply connected. So the set of regular values is always not simply connected. And that means we should expect to have quantum, and Hamiltonian monodromy. All right, so it's time to move on to the quantum part. So yes, we need to quantize the Lagrange top, and again, this is somewhat classical. I mean, the symmetric top certainly without potential is easy to quantize, and it has been quantized in 26. So basically, right when quantum mechanics appeared, and it turns out that that leads to the hypergeometric equation. and the eigenfunctions are, in fact, Jacobi polynomials. This is a paper in German, but it's kind of explained in Landau-Lifshitz quantum mechanics. So, but the Lagrange top has this extra linear field. In the physics literature, this is usually referred to as the Stark effect, because it is actually a rotating molecule now that is affected by an electric field, and that is referred to as Stark effect. And that has been quantized in 55 and then also numerically computed spectrum in 63. This monodromy that I mentioned already has been studied in 2003 by Poisson and Roberts. Again, because the image is not, the image of the energy momentum map is not simply connected. The action variables are not globally defined. And therefore, by semi-classical analysis, we also get quantum numbers that are not globally defined, and that is referred to as quantum monodromy. Okay, so what is the Schrödinger equation now? So here's again the classical Hamiltonian. Now, as I said, we do need Euler angles to do canonical quantization. And if you write this in ZXZ Euler angles, that means now we're writing our orthogonal matrix R as a product of 3 rotation matrices about the Z-axis, X-axis, and Z-axis with angles phi, theta, and psi. And then you go through the standard process of writing down your Lagrange and your Hamiltonian. You end up with this expression for L squared. That's the essential term in our kinetic energy. And I have already here replaced my canonical momenta p phi and p psi by integers, and I'll call them m and k. And well, why is that so? I already showed you that these quantities are action variables, right? They are generating, as Hamiltonians, periodic flows with period 2 pi. And now if you quantize them, then basically you just get a partial derivative with respect to phi or psi. And then because it's a periodic flow, the boundary condition is just that, that this should be a function that is well defined on that circle, right? And so you get e to the y function, therefore is e to the power 2 pi I. Well, maybe you have an h bar here. I set h bar to 0 times an integer. And so there we go. So the classical actions, the global actions, they quantize as integers. And now here's the quantum Hamiltonian, where all these hats just say, well, you should replace the canonical momenta, and there's only one left because these are already quantized by the derivative with respect to theta times I times h bar. There we go. So canonical quantization is this. P theta goes to I dd theta. And then we do another transformation of variables where we say z is cosine theta, and then you end up with this equation. In which way does this determine the spectrum? Well, this is it's a singular equation, or it has singularities at these poles of these rational functions in z at plus minus 1. You require that the solution is smooth at these points. And that is only possible for special values of this accessory parameter. And that gives you a discrete spectrum. I guess these twiddles, I didn't write down the formulas. They're just kind of absorbing h bar and I1 and some constants in it. Oh, and also the delta is absorbed in this e because it's just a shift by an integer squared. Right, and so this is now actually already, in some sense, the Confluent Heun equation, but not in its standard form, but in a particular symmetric and self-adjoint form. So let me talk a little bit about the Confluent Heun equation now, and explain where it comes from. So Fuchsian equations are, in general, linear ODEs with rational coefficients, and when there are singularities in the coefficients, then you have singular points, and you call a singular point regular when the solutions at that point have algebraic growth at worst or bounded by algebraic growth. And then you say Fuchsian equation is one where at all poles, including infinity, I mean, so you do this on the Riemann sphere, they're all regular singular points. And yeah, actually, this is just a historical remark that when this is Lazarus Fuchs, in fact, studied these, he was actually interested in abelian integrals because it was observed that abelian integrals have this property. So Fuchsian equations historically come from looking at abelian integrals. And that's interesting in this case because those are the action variables, right? The action variables for the Lagrange top or for most integral systems are abelian integrals, and they satisfy Fuchsian equations. But in this context, this Fuchsian equation, the Heun equation, appears from the quantization, right? So I'm not looking at the Fuchsian equation that has the action variables of the top as a solution, which one could do, but that's not the equation we're talking about. Okay, so what's the kind of simplest non-trivial equation of the Fuchsian class is the hypergeometric equation, and it has 3 poles, and they can be moved to 0, 1, infinity by Möbius transformations. And then in addition, there are 3 parameters that determine the indices, the local behavior near these poles. And Heun is just 1 level up. Now you have 4 poles. You can only normalize 3 positions with a Möbius transformation. And so the 4th pole has position A. That gives you an extra parameter. That's the 1 here. Each pole has indices associated to it. So that's 4 parameters. And then there's this extra accessory parameter, which for us is the spectral parameter. Heun is not very well known, I would say. So I thought I'll give you a little bit of background. So he lived from 1859 to 29 in Germany and did his dissertation in mathematical physics in Göttingen in 1881 and became professor of the newly created technical university in Karlsruhe in 1902. And the paper that is relevant for us is Mathematische Annalen 33 in 1888, where he wrote about Riemannian functions of 2nd order with 4 branch points. We don't use that terminology these days anymore, Riemannian functions, but this is the Heun equation, so generalizing the hypergeometric equation. And as with the hypergeometric equation when Gauss studied, so it starts from the solution, right? So what he did is basically said, okay, I want to have these branch points and I want to have a kind of linear transformation when you go around them. And therefore, the solutions are like this. And then he says, oh, and they satisfy a differential equation as well. Right? So it's, that was the approach. So, okay, now Confluent, now you have to take your poles and coalesce them. And this we have actually definitely seen in Harini's talk, but on the Painlevé side, where you start with P6, and the first degeneration is actually P5. And that is the coalescence that is also relevant here, where we coalesce just 2 poles. So the pole with position A goes to infinity, and then we're left with 4 plus 1 parameters. So this is the parameter A has disappeared. Okay, and now the theorem I promised is very easy now to prove the separated Schrödinger equation or Schrödinger operator of this harmonic Lagrange top, harmonic meaning with a quadratic term, can be transformed into the general Confluent Heun equation. And it's a straightforward computation. You need a Möbius transformation, and then you have to adjust the indices by multiplying your dependent function by certain powers, and then you end up in the standard Confluent Heun equation. And what is interesting is that after that operation, well, or even before, in fact, the indices at the poles of this equations, they are exactly, well, up to dividing by 2 here, these global quantum numbers, m and k. Right? So the indices have a very important physical interpretation in this, if you come from this derivation. Right? M and k are the quantum numbers of the angular momentum around the z-axis, and the angular momentum about the body axis. Then we had two more parameters in the Confluent Heun equations, and that's the C1 and the C2. And that's why we introduced the C2 in the first place, so that we would have enough parameters to get the general equation. And the eigenvalue of the energy is the accessory parameter of the Heun equation. Right. Okay, so I guess I wanted to close with a couple of remarks, and also one remark about Painlevé in the end. So when you look up what's the physical application of the Heun equation, then you end up with this paper, as you referred to, perturbation theory near a Kerr black hole, and that was done by Tucholsky, and in that setting is also known as Tucholsky's master equation, or as the general spheroidal wave equation, or the Confluent Heun equation, all the same thing. And I was looking for a reference that would say the Lagrange top is the case of the Confluent Heun equation. I could not find this reference, but if you do know this reference, please send it to me. In a way, that was the motivation to write this paper and say, well, actually, there are these two classical things, Lagrange top, Heun, Confluent Heun, and they are actually related. And if you add this quadratic parameter in the potential, then you actually get the most general Confluent Heun equation from quantization of the harmonic Lagrange top. And so I would claim this is a very natural physical application of the Confluent Heun equation. Of course, black holes is also cool, right? So, I mean, that's another application of the Confluent Heun equation. However, they're missing one parameter. So they're the Kerr black hole. I guess they don't have this freedom of just adding a potential as we do. Right. Okay. Yeah. Just a quick remark. I guess computing the spectrum. In the end, we did want to compute the spectrum, and that was not in the literature. Well, because it had been done only with the linear coefficient, but not with the quadratic coefficient. And so at this point, what you do is you go back to the hypergeometric equation, which in my notation is this. It's the spherical top. That's the hypergeometric equation, and that has solutions that are Jacobi polynomials. If you are on SO3 in the physics literature, instead people use these Wigner D functions. So they're normalized in a slightly different way. So use this as a basis. And then your H0, that's the L squared, is just diagonal in that basis. And the eigenvalues are J times J plus 1. So you get a diagonal matrix with these entries. And the diagonal is shifted by K squared, but K is a constant. And that's why we tended to ignore that term, right? It's a trivial shift of the whole spectrum for fixed K. Then C1, so this is cosine theta. Now you have to basically just find a representation of cosine theta in terms of Wigner D functions that had been known. And then we just observed, well, here we have cos squared theta. And if you look at the second Wigner function, then you get an explicit formula for H2 in terms of H1. So, which is kind of cute because it's pentadiagonal, right? This is a square of something tridiagonal. So it's a pentadiagonal half infinite matrix that gives the spectrum. And so here are some pictures of the spectrum. The classical energy momentum map is kind of the boundary by semi-classical quantization of the spectrum, right? These dots are the joint spectrum. And these lines come from the energy momentum map that I discussed. And I guess in these pictures, you can observe this quantum monodromy, but let me not go into that. Just a couple more pictures for the different cases. These are these hyperbolic two tori, where the spectrum kind of reorganizes itself when it goes into this triangular tube. And these are just slices because it's very messy, I guess, to show a picture of a joint spectrum of three commuting operators. That's a bunch of dots in R3. It's impossible to understand. So that's why we just show some slices here. Well, I guess I'm out of time, and I should thank you for your attention. And but I will advertise that I do have a slide about the connection to the Paine-Levé equation, if anybody wants to ask about that.
Thank you, Holger. So any questions about the Paine-Levé connection?
So you know exactly what I'm going to ask, right? But I also had a couple of other questions. Maybe I can come back to it, but please show us what you meant with your teaser.
So, I mean, this is a paper by Slavianov in 2000, where he basically did the following. So you said, take actually any Heun equation. So you can forget about Confluent Heun. So start with the Heun equation, which is this differential equation. D here is this derivative, second derivative, first derivative, no derivative. Applied to y is lambda y. Lambda, okay, I called it E, now it's called lambda. So this is just the equation again. And P, these P's are polynomials. And they depend on some parameter T. In this case, T is a parameter, which is actually, I call it A, it's the position of the pole. Now, okay, you have to write down the correct degrees, but the Heun equation or Confluent Heun equation can be written in this form. And now what he says is now you should, I call this dequantize it, right? Remember how I arrived? I started with the Lagrange top and I said, let's quantize it. And I came to Heun, right? Now, apparently this process is not commutative, right? So because now we're taking Heun and we're dequantizing it according to Slavianov. So we replace this D by a P, right? So the quantization, remember, was to replace P by I. Okay, up to I, this is the same, right? So I replace this by a derivative. I will replace the derivative by P, and the variable Q now becomes the Z is just a Q multiplication by Q. And then let's write down a Hamiltonian. That's this Hamiltonian here. That is now a classical Hamiltonian, which is made out of this out of these terms. And then if you now Legendre transform this to a Lagrangian and write down the Lagrange equation, then this is Paine-Levé 5.
Yeah, and, I remember that.
I didn't really want to include it. I mean, because this, I don't understand this at all, right? So in some sense, you would say, well, this should be the Lagrange top now, right? Because it's just reversing the process where how I arrived, right? But of course, it is not, right? But,
there's something intriguing there underlying that. Yeah. I have a couple of other questions, but maybe I'll let other people ask and then I'll come back to you.
So anyone else want to ask some question before Nalini
get? I have two hands, Vladimir.
Yes, I have a question. So, to what extent the monodromy of this equation is understood? Monodromy group, I mean connection coefficients in particular. So you have different bases of solution, and sometimes for hypergeometric equation, you can explicitly calculate the connection coefficients for all rigid equations. So to what extent it is understood?
I think that, well, that I don't really know the full answer to this because I haven't studied that, but my understanding is that this is the other connection to P5 again, right? Because if you want to study the monodromy of the Heun equation, then one way to do that is to use tau function of the corresponding Paine-Levé equation. And people have actually done that, in particular in this context of the black hole, where you actually have two Heun equations. You have one for the angle and you have one for the radial part that come from kind of separation of variables. And the radial equation is a scattering equation. And to handle that, what people have done is exactly use Riemann-Hilbert techniques and tau functions from Paine-Levé to actually compute this. And there it was relevant to actually solve the problem. I think for the Lagrange top, I don't see a need to do this, but it would be interesting to understand, well, what we could learn from it. So I'm not quite sure if that answers your question, but
yeah, I have a practical interest. So we use this equation where you can understand. So the simplest case, you calculate the connection coefficient explicitly. Okay, that's hypergeometric equation. But you can deform the hypergeometric equation at extra term. So and in that case, you cannot calculate the connection coefficient explicitly, but you can write some nice functional equation for them. And this way you connect differential equation to integrable quantum system like lattice models. Okay. Well, I'll make a comment tomorrow in my talk, but that's what I'm searching, equation where you understand the connection coefficient.
I mean, the expansion in terms of hypergeometric solutions, I mean, we also used explicitly in the computation of the spectrum, right? But yeah, but it's a slightly different question, I guess, if you ask for the monodromy, right? So, but it seems very much related. Yeah.
Thank you. So maybe one last question before we close today's session.
Yeah, I have a hand raised here by Francisco.
Nalini had a question.
No, there's also one from Francesco. Please go ahead.
Okay, thank you. Hi, everybody. I have a little question about the choice of coordinates that you mentioned that at the beginning of your talk. And you choose special coordinates rather than body coordinates. And can you justify a little bit more your choice?
Well, it's because for a symmetric rigid body, it works. Let's say it that way, right? I would say naturally to stay in the spatial frame is a good idea, right? If you can, but if you don't have a symmetric body, you can't, or at least you get something that is very complicated. But if you do have a symmetric body, then I would always say, yes, you should stay in the spatial frame because it makes things actually simpler.
Okay, so in this case, you are free to choose any of those possibilities.
You could have done it in the body as well. But for example, if you look at the Hopf bifurcation and you compute eigenvalues of these periodic orbits, if you're in the body frame, you're in a rotating coordinate system, and the rotating coordinate system changes your eigenvalues, right? So, that's why, if you can, you should stay in the spatial frame.
Okay, thank you.
Yeah, okay.
So can I just quickly ask a couple of questions? One is, as you know, there are three integrable tops, and Lagrange is the middle one. The simpler one is the Euler top, and then the more complicated one is the Kovalevskaya top. So I'm assuming that you could also apply this strategy to those cases. And I'm wondering whether they lead you to particular types of Heun equations and where you go from there.
Question. So, I mean, Euler top again has been done classically, I mean, in the 20s, and leads to the Lamé equation, and the Lamé equation is a special case of the Heun equation. But Kovalevskaya is so much more complicated that I'm not aware that it has even been written down as a kind of simple Schrödinger operator. I mean, I guess the issue is that standard separation of variables doesn't work for Kovalevskaya. So it is integrable, but you maybe shouldn't expect to arrive at a single equation somehow. So I'm not sure. I don't think it has been done for Kovalevskaya.
But I think that there's intriguing possibilities.
Definitely, yes.
Yeah, so that's exciting.
Let's thank the speaker again and everyone who asked questions.